Testing.
Frank, can you hear me?
Yeah, I'm back on.
Okay, so I think we're actually right now we're starting to record right now. So you'll be on here. I think you're live right now. So I just wanted to make sure I can hear you.
Okay.
We'll start here in a couple minutes here.
Sounds good.
Thanks. If one of the audience members just can verify that you can hear me properly, please just type in a quick question that you can hear me. Thank you. Thank you very much. Frank, you want to, can you hear me? I can't hear you talking, Frank. Can you?
How about now?
Okay, there we go.
You got the right one slide up?
You got the right one slide up. We might as well kick it off here. I'm sure people come on and add on as we go. So go ahead. I'll let you take it over, Frank.
Okay, thanks very much. Good afternoon, and thanks for joining us on today's webinar. I'm going to be focusing on a company called Secureaire, which is basically all about energy-efficient particle control. And we're focusing on the dominant transport mechanism for particles. So that's what Secureaire is about, and that's what we'll be discussing today. So the company is based upon a couple of different patents, as you can see in the second slide. The first patent is the PACT, Particle Acceleration Collision Technology, and that's primarily where we will be spending most of our time today. We will go into the third patent as well. Secureaire is a privately funded company founded in 2004, and it was founded by a gentleman that spent basically 18 years at IBM Corporation designing computer chip circuits and how to keep clean rooms in fact clean. The company first commercialized its products in 2006. There are numerous case studies available online, and the nice thing about the company is that they actually did have a controlled product release. So they didn't put a lot of product out there on the market. They took their time, they slowly put it out there on the market, and now we're basically ready to go into the commercial markets in a large way. So indoor air quality and continuous improvement. You don't have to go too far to notice or know somebody that has asthma. In fact, 4 of the 10 chronic illnesses today are actually respiratory in nature. So you have asthma, bronchitis, sinusitis, and allergies. The next thing is nosocomial infections. And I'm not sure if everybody knows what a nosocomial infection is, but that's basically a hospital-acquired infection. So it's something that you didn't go in the hospital with, but it's something that you got while there. And the CDC puts nosocomial infection cases every year at somewhere around 2 million, which if you think about it is pretty high. So that translates to roughly about 2 for every hospital bed that we have in the country. You have a greater than 10% chance of leaving the hospital with something that you didn't have when you went in. Annual burden to the healthcare system, somewhere between 20 and 40 billion. So the question is, are airborne sources a participant in hospital-acquired infections? And the estimate for that is somewhere around 10 and 20%. However, the biggest airborne transmitted disease in healthcare is actually pneumonia. And if we look at the number of annual cases of pneumonia reported in hospitals, it's roughly about 120,000, and typically about 1/3 of those patients actually perish. So I think the bottom line is if you don't have to go into a hospital, don't. So let's move on to small particles, transport mechanisms, and how they actually tie into ASHRAE's 52.2. So if we think about small particles and a cubic foot of air, we roughly have about 3 million particles less than a micron size in a cubic foot of air. Yes, that's definitely a big number, and the reason to be concerned is that small particles are actually the ones that get deeply entrained into our respiratory system, and if they're bad actors, can cause us a problem. The issue with small particles is that the smaller they are, the less likely they are to actually get to a filter. So the issue is small particles less than a micron in size only get captured if they actually get transported to the filter. There are 2 major transport mechanisms that influence particles, one being airflow and the second being electromagnetic fields. The main transport mechanism for particles 1 micron and smaller is not airflow. It is actually an electromagnetic field. So high efficiency filters, what do we associate them with? Well, we associate them with better capture, yes, but also higher fan energy usage. And that's a direct measure of the higher static pressure. And remember, only high efficiency filtration captures particles that get brought to the filter by airflow. So Secureaire is in a unique position in that we can both measure and remove the full range of airborne particles and pathogens. So now, let's look at that 1 micron size and see if we actually should be concerned. And as you can see in the slide, for small particle mean diameters, a lot of the particles that are 1 micron and less, or around 1 micron, are very bad actors. So we need to be concerned about those small particles, and we need to have a way to actually quantify that they're there and also be able to remove them. Okay, so Secureaire and dominant transport mechanisms. As you can see on the left of the slide, we've got a lot of particles that are less than a micron in size, roughly about 2.2 million here. And those particles are largely controlled by electromagnetic fields. What we want to do here is actually move that line from airflow to include those particles. And if we can do that, we'll have a better chance to actually capture those particles and remove them from the air. So what we're talking about here is that Secureaire makes the dominant transport mechanisms airflow away from electromagnetic fields. So that's a key, and that's probably one of the most important slides here, is that we now have a technology that can actually unlock the hold that electromagnetic fields have on those particles and actually get them into airflow so that they can actually be removed. Okay, so if we were to look at the platforms that Secureaire offers today, we can build up our systems in an air handler that you can see in the first depiction. The second thing is we do have an induct system, which is good if you're looking at just purifying the air of a room. We also have a portable device, which can be used in various different ways. One being, for example, if you have a remodel in a healthcare institution, that would be a nice way to keep the air clean from where the construction is going on and where the patients are. So it's a good insurance policy from an air perspective. The other thing that Secureaire has is actually an air quality monitor. So it is actually a very simple device that can actually measure the amount of particles that are in the space where you are. And that's very important because we're not looking at the quality of the air inside of the air handler. We're actually looking at the quality of the air where we are in the room. And that's really what we need to be most concerned with. Another platform that Secureaire has is the ACS system, which is a single-pass, high-efficiency device that, in fact, has the ability to kill whatever's being captured. So, to go into a little more detail on some of these product platforms, first, the AQM100 Air Quality Monitor. Again, a very easy device to operate. It can help monitor the levels of bacteria, viruses, and any other contamination that's potentially in the air. Just some of the features, a very easily read LCD display. It measures down to 0.4 microns. And that's very important. That 0.4 micron channel is actually the small particle size on ASHRAE's 52.2 test. So we're actually getting the most challenging particle size for ASHRAE's 52.2 test. So that's a key feature of the monitor. Again, very easy to operate, connection to a standard wall outlet. You can communicate via a number of different platforms, download the data. It's a very, very good device, and of course, more importantly, it provides you the ability to have not a third-party test, but actually a first-party test, because you can test it right there, resident in any space, and again, very easy to use. So, the Secureaire technology is based on very simple properties. And what we found in the past is that if you can't explain it very simply, then it's just not easily understandable. So what we're trying to do here is to just show you that from a particle science perspective, likes repel, basically 9th grade physics, and unlikes attract. That's the basis for the Secureaire technology. We want to harness those two simple principles to actually get us to a dominant transport mechanism being airflow. So from a PAC perspective, PAC does two very unique things. The first thing it does is that it actually conditions particles and makes them want to come together. So if you have positive and negative, you want to make them come together and become larger. The second thing it does is it actually forces the conditioned particles to collide. And of course, once you get particles to collide and attach, they're held together by ionic bonding, and it's very, very difficult to get those particles away from each other. So more simply, PACT is a device that makes every filtration device more effective. So if we look at the slide, basically if you have a standard filter, it takes some particles out, yes, and some, of course, get through. If we put a PACT system downstream and use those particles getting through, we actually agglomerate those particles via electric charge, and those particles actually come out of the PACT system in a neutral state. That's very important, because if you have particles in a neutral state, when they go back into a room, they will actually attempt to break down the electrical charge of smaller particles, and they'll actually adsorb or absorb what's in the room, therefore making them larger and therefore making them easier to remove. So we basically take an ordinary filter, add a PAC device, and we make that filter better. The question is, how much better? Well, depending upon the filter and depending upon the application, we believe somewhere between 3 and 6 MERV ratings, which, of course, is significant.
Frank, what is the pressure drop?
On to a little more.
Frank, what is the pressure drop through the PAC system?
And that's a very good point, Mike. The pressure drop through a PAC system is actually virtually zero. It's measured, we've measured it down to 0.02 inches of static. So from an additive sense and from a fan horsepower standpoint, it's actually negligible. Okay, so let's start now by looking at some data from the PAC system. So you can see in this slide that we've got a pretty good particle clip going on across the top, and then we turn one of our portable systems on, and at a volume of basically 2,000 cubic feet, so it's a small room, and we've got a very, very high air change rate. We notice that after about roughly 20 minutes, we've cleaned up the room at about 81%. So we've really taken a bite out of those particles. Now, of course, you would say, well, that's a very high change rate from an air perspective. So what if you had a bigger room? Well, of course, we looked at that. We looked at a room that's basically 4 times the size, and we cut the air change rates down from 60 to 16. And lo and behold, roughly the same thing happened. So what we know today is that the PAC technology is very effective in the recirculating air room mode. It works very, very well. So now, a little more data. We had an interesting case study at the Lake Tahoe Surgery Center where we were looking at the removal of particles. As you can see in the graph, the red is the system without the Secureaire, and the blue is the system with Secureaire. So we basically knocked down a lot of the particle intrusions that were occurring in the room. And this actually was a third-party test. So the surgery center actually hired someone from the outside to actually perform the study. Now here's where it gets really interesting for us. TVOCs. We actually weren't aware that they were actually looking at the measurement of TVOCs. And we were actually very, very surprised and happy to see that not only are we now affecting the removal of particles, but we're also affecting the reduction of TVOCs. That's pretty important from a quote-unquote filter device perspective. And we actually got a letter of testimony from the head surgeon at the center, and while they had low hospital-acquired infections prior to the date of the PAC system install, they went to 0. And they held 0 for a little over 3 years. 0 hospital-acquired infections in an orthopedic surgery suite is very, very impressive data. So we'll take it a step further. The same surgery suite in the summertime had a number of forest fires. And all during those forest fires, basically, the surgery center had no effect of smoke. Now, as the story goes, there was also the Lake Tahoe Hospital, and when the fires were going on, they had problems in the hospital. So what happened was the hospital actually called the rep that had the PAC system installed in the surgery suite, and they were asking him why the hospital was full of smoke. And his response was basically, well, your hospital is full of smoke because you don't have the systems in the hospital, they're in the surgery suite. So it was nice to get another additional data point on the PAC technology from the perspective of not only is it now effective on particles, TVOCs, but we've now added smoke. So again, a little more data and support for the PAC technology. IBM in Silicon Valley basically went for a recent build-out of a building, and they applied for a LEED Gold status. The problem is that when they went into the building to check the air quality, they didn't meet any of the minimum allowable concentrations for LEED. And that was for formaldehyde, particulate, TVOC, PCH, and carbon monoxide. So what happened was, because none of the criteria could be met, rather than go through a 2-week 100% outdoor air flush of the building, which, by the way, was not practical considering this was midsummer, what they did was employ a number of portable PAC systems for 3 days. And after that implementation, the third-party testing facility went in, took the air samples, and very successfully reduced all of those categories and got the certification for IBM. Again, just further added support that the PAC technology is not only unique, but in fact it works very well. So one more data point. Secureaire was being looked at by a large food plant in western Michigan. They had employed MERV 11 and MERV 14 filters. And their curiosity was to see how good does, in fact, the PAC actually work in our system, and what would happen if we did multiple installs. So what happened in the first install was they put one PAC system before the MERV 11 and MERV 14. And in fact, they got improvement. And what you can see here is that the MERV 11 improved more dramatically than the MERV 14. They went next to a in-series test, and in this in-series test, you can see that both filters actually looked and performed much better from a MERV perspective. You're looking at a close performance to a MERV 16 from both a MERV 11 and a MERV 14. So again, this is just further support in that the PAC technology, we believe, is very, very efficient at what it does, and it makes any type of filter look better in any type of system. So just a summary for the PAC technology itself. PAC basically treats particles and dissolved gases equally. TVOCs, carbon monoxide, carbon dioxide, particulate matter, smoke, and odors. It doesn't care. It doesn't care what it is. Everything gets treated equally. PAC conditions particles to collect other airbornes. PAC is basically a particle control device, and it's the only one out there on the marketplace today. So now,
Frank,
what we'd like to do is...
can you, what kind of footprint are we talking about from a, how wide is that unit, and where does it slide into an air handler? So how much footprint do we need for an air handling system, for that PAC system to be employed?
Okay, so for that PAC system, and remember, the PAC system is really, the real application for it is in a recirc mode. So that's really where the niche is for that technology. But if we think about how much room we need, it's basically 3.5 inches in airway length.
And do you need any serviceability of that piece?
That piece basically does not require service.
Okay, so you can actually put it in a 12-inch compartment, like an access section of any air handling unit system.
Absolutely.
Okay.
Absolutely. Okay, so next we'd like to talk about the ACS system, which is the high-efficiency single-pass device. So we'll start out with a couple of facts from an air filtration standpoint. So basically, again, we've covered this before. For most particles, electromagnetic forces and not airflow control the movement of the particles. And again, what we want to do is convert that. We want to make airflow the dominant transport mechanism. Okay, what we're showing here in the picture is the downstream side of a HEPA filter. And what we've identified in that little circle is basically mold. So we're now looking at the downstream side of a HEPA filter with mold on it, which means what? Well, basically at 250 feet per minute, that mold on a downstream side is becoming aerosolized and is now part of your air supply. And if that can happen to a HEPA filter, we need to be concerned about how we treat and how we utilize filtration, and actually do we have the right tools in our supply. So the capture and deactivation of health-degrading organisms is very important, and it is necessary in filtration. Of course, filters must have the ability to collect small particles, and we want to be concerned about fan energy as well as airway length, which we just mentioned. In Secureaire's ACS filtration purification system, this device does employ similar pack technology for a single pass efficient filter. Although it's not 3.5 inches in depth, this one is 11. But if you look at other devices that are out there on the marketplace, we're significantly smaller in airway length depth than anything else out there. So from today's perspective, where is the ACS filtration system? It has a MERV rating of 14. It activates and kills up to 99% of what's captured from a biological standpoint, low static pressure, and you have the same packed effect from particles that exit the filter. They have the potential to go in and clean up as long as there's some mixing in the air involved. So again, for simplicity's sake, and if you can't explain it easily, it's probably magic or unexplainable. But with the ACS system, we basically do three things. We use the charge behavior model that we talked about earlier, unlikes and likes. So we're using charge to help particles get bigger and to remove them. We also use here polarization. And polarization is just basically making particles become more attractive. The last thing we use is ionization, and ionization helps to put charges on particles that are positive, neutral, or even negative to make them easier to be captured. So again, we're trying to break it down into three easy steps that the ACS system employs in its technology. So if we look at the ACS system from an expanded view perspective, there are three components across the bottom. There's the PCU, the collector, and the collider. And the collider is the piece that's very similar to the pack system that we discussed earlier. So if we just look at the PCU first, it basically ionizes incoming particles. And we do that basically with charge. You can have positives, negatives, and neutrals. And typically what we want them to do is to all come out of the other side with a neutral charge. The collector, which is where we capture the particles. So after they've gone through the first stage, they come out negative. We then put charges around that collector device so that the particles are more easily captured. We're creating an electric field around the filter itself. We're creating a polarized field on the filter fibers in the opposite direction, which makes them stronger. And those particles will travel through, basically, regardless of polarity, get stuck to the filter fibers and become captured in that matrix. We also have to remember that filters are not 100% devices, so every now and then something will get through. Now again, remember that we have fields around that collector device. Those fields are high voltage, low current, and the charge density is probably the most important thing. Charge density is the part of it that actually gives you the ability to kill anything that's viable. So that's why the system has the ability to kill. Okay, so the collider is the same device as the PACT. It's just on the end of the entire ACS system. It basically changes polarity over time, and it creates that ability for particles to collide and actually get larger and therefore easier to move. We can talk about more depth here, but we're using not only DC voltage, but we're also using AC voltage. And that helps that collision process and those particles to collide and be easier to be removed. Again, here, along with the PAC device, we don't care what it is. We don't care if it's a gas. We don't care if it's an odor. We don't care if it's smoke, bacteria, or a virus. It will work on each one of those as they look the same. Okay, so again, kind of putting it all together, the PCU basically ionizes particles that go through the device. The collector, that's the part that actually collects what's coming through the challenging air. We have an efficient filter, low static pressure, very strong fields to help deactivate, and even if you have no power, you still have a MERV 10, MERV 11 filter device there. And of course, from a last part, the collider, that is very similar to the PAC device, and it helps to make airflow that dominant transport mechanism. One last set of data. If we were to look at actual counts in a room and how different MERV devices would perform, looking at the top, basically a MERV 8 device at half micron particles per cubic foot, you're basically looking at 100,000 of those particles being remnant in the room. Even if you're recirculating the air, that's as good as it gets for a MERV 8. A MERV 12 does have the ability to reduce that, and if you look at the green line, the ACS, you're looking at bringing those particle levels extremely low into double digits or even single digits. And that's within a 5-minute recovery time. So the PACT system, which is the basis of the Secureaire technology, is very, very good at removing, changing that dominant transport mechanism from electrostatic or electromagnetic fields to airflow. And that's what Secureaire is actually all about. So we've kind of been through the ACS platform now. It's high efficient. It has the ability to kill, low static pressure, and it has the ability to help clean up the other rooms with a return airflow. So too, a couple of marquee installations that currently employ the PACT. The first is the Liberty Memorial Museum in Kansas City, where it keeps the museum air clean and all of the art that's in there. The second building you see to the right is the Lake Tahoe Surgery Center. The bottom left is California's Central Plant, which helps keep the air clean for the employees that operate the plant. Bottom right is the Federal Bowling Building in Kansas City. And the center picture actually is the San Joaquin County Administration Building in Northern California. So to kind of bring it full circle, Secureaire has the PAC technology. It has an induct system. There's a portable system, the air quality monitor to help validate and offer a first-party test, and the high-efficiency single-pass ACS system. And Secureaire, again, a company that provides both measurement and the ability to treat indoor air. And of course, translating into the ability to keep air handlers fan-sized correctly and efficient from a indoor air quality perspective.
Frank,
Right.
and one of the key things that we want to note is at TEC we've actually purchased a portable APS unit and also the air monitor. So what we'd like to do is obviously show you this in person for those folks on the line, and you have other members of the company that you're working with that want to see this technology also work, because you want to tell them a little bit about, we did this in our meeting room where we turned this on, and what do we do, Frank? We went from how many particles per cubic foot?
During our initial training session, what we like to do when we actually do these Secureaire trainings is have a air quality monitor there and also a portable unit. And in the case of TEC's training, I believe we registered somewhere close to 4.4 million particles on the small channel. And within roughly about 35 minutes, we had reduced that high concentration in greater than half. So just adding credence that the system absolutely works. We had a lot of other dynamics going on in that room. It was probably a little oversized for the system, people going in and out, but definitely a support for the technology itself. And seeing it right is believing it. I mean, that's the best way to show it.
And that's really the reason, you know, Frank, in my opinion, is one of the best filtration experts in the industry. That's why we teamed up with him with this technology. And I love the fact that you can actually see the performance live when you're looking at and doing the training and getting the presentation in the room. A couple of questions here we had. So Frank, I'm going to just rattle off the questions if you want to answer them, okay?
Sure.
Okay. What does PACT stand for?
So PACT is Particle Acceleration Collision Technology.
Okay. And then we had, what kind of power requirements can we expect with this device? And then, and then does Frank have information on the energy evaluation balancing the power required of the device and the fan power reduction coming up and the ROI of the device? Very good question.
Okay. So the answer to the second one is yes. We definitely do have the energy calculator available, and it's basically a straight pressure drop calculation, and it does take into consideration the energy that's burned. From an energy usage standpoint for the PACT, the energy usage for the PACT is extremely low. I believe that we're looking at, for an 80 an 80,000 CFM application, you're looking at roughly 150 watts, so extremely low. On the single pass high efficiency system, you're looking at roughly 30 watts per 2,000 CFM. And those numbers are also on the literature and product data sheets.
And the last question here, how does the air temperature and air humidity affect performance?
We don't care about air temperature and we don't care about humidity. And just to expand on that a little bit, early on in the presentation we talked about how Secureaire was more or less tentative at putting their first installs out there. One of the things that they learned was that even though people tell you that there's no moisture in air handlers, we know better. And they did experience some water issues with the pack, which led to a very important development in that the device as it stands today is definitely water resistant. We'd like to say waterproof, but somebody would prove us wrong. And the reason why we're very confident in that perspective is that all of our devices are manufactured in the U.S. Everything. The air quality monitor, the PAC system, the ACS system, everything's actually manufactured just outside of Tampa, Florida. And that manufacturing facility actually does contract work for the military, and their expertise is in electronics, and those electronics could be in the Sahara Desert 1 week and then get transferred to Nova Scotia the next month. So from a extreme perspective, we have a very, very good handle for the manufacturing of product and the extremes to which it can be employed. So temperature doesn't matter, neither does humidity.
Okay, how does this technology, Secureaire, differ from past electrostatic technology?
There are numerous differences. The thing that probably puts Secureaire above all others is the electronic circuitry. I believe there's no product on the market today that has the advanced electronic circuitry that Secureaire has, and that's not by accident. If you remember, the founder of Secureaire spent 18 years at IBM designing computer chip circuits and modifying processes and improving ways to make them. So that's one thing, but that's a large thing. In addition to that, smaller footprints, very important. If you know how to collect particles and capture them, then you can actually effectively treat them. And in this case, we do both. So we have the ability to capture, and we have the ability to inactivate. And if you look at other platforms out there in the market, nobody has that sewn up. And I believe Secureaire is in the best position. And the other thing is, why hasn't anybody come out with a simple, easy-to-use air quality monitor to measure performance? As engineers, as designers, we specify humidity, we specify temperature, we specify air change rate, and then we put an ASHRAE 52.2 filter in there and say, okay, it must be good, but we never check it. So I think we want to be the company that changes the paradigm, that says, hey, we really don't care if you use Secureaire's filter products, but at least know where you are with what you have. And we give you that ability. So a long-winded answer, Mike, but I think we touched on a couple of key points.
And I think that's it for questions today. If anybody, we're going to have Frank in town in the next within the next month or 2 months here, and when he does come on board, when he does come out here, if you're interested in seeing him in person, discussing projects, send an email to myself, Mike Smid, or Ryan Hoger on the presentation. Whoops, I got one more question here. Are there any micron standards for hospitals or commercial spaces similar to clean rooms?
That's an excellent question. And the short answer is no, there aren't. And but the to be determined is there should be. I think that's where we should be going, especially in operating suites and operating rooms. There basically should be standards for particle counts. I believe we would solve a large part of our hospital-acquired infection rates if we had specifications for the number of particles that had to be in the room. Excellent question, though, and we're lock, stock, and barrel agreed that that's where the industry should go.
Okay, I think that's it. I'm going to, again, if you want to contact myself or Ryan Hoger, I think you get the email from Ryan Hoger. So if you want to contact myself, mike.smid@tecmungo.com, or Ryan Hoger, send him an email and say, I'm interested in seeing Frank in person. Let us know. And then I think that's it. But thanks, everybody, for joining us today. And Frank, I think we're all set, and we'll sign off.
Okay. Thanks very much, everybody.
Thanks.